Hello, this is Chemistry International AS Levels, Unit 2 at Excel International Full Revision Guide. So starting with topic 6, energetics, we have bond enthalpy, which is the energy required to break 1 mole of gas under standard conditions, which is 100 kilopascals and 298 Kelvin. Then we have calorimetry, which is the process of measuring amount of energy absorbed or released during a reaction. We have endothermic and exothermic reactions. Endo is a reaction that takes in energy from the surroundings, so temperature to surrounding decreases, and energy needed to break bonds is more than energy released, forming new bonds. We have delta H, which is a symbol for enthalpy change, and it means that heat energy change measured under a constant pressure. We have exothermic reactions, which is reaction that releases energy to the surroundings, so temperature of surrounding increases. So energy needed to break the bonds is actually less than energy released from making new bonds. We have Hess's law, which says enthalpy change of a reaction is independent of the route taken. And we have mean bond enthalpy, which is enthalpy change when 1 mole of a specified covalent bond is broken, averaged out across a range of compounds. Then we have standard condition, which is usually 100 kilopascals, and stated temperature, which is usually 298 Kelvin. We have standard enthalpy change of atomization, which is enthalpy change when 1 mole of gaseous atom is made from an element in a standard state under standard conditions. We have standard enthalpy change of neutralization, which is enthalpy change when solution of acid and alkali react under standard conditions to produce 1 mole of H2O. Standard enthalpy change of reaction could be used for any sort of reaction. It's the enthalpy change of quantities of substances in a standard state that react completely under standard conditions. Then we have enthalpy change of combustion, which is enthalpy change when 1 mole of a substance is bound in excess oxygen in standard conditions. Then we have standard enthalpy of formation, which is the enthalpy change when 1 mole of a substance in standard state is formed under standard conditions from its elements under standard conditions. Then we have topic 6, energetics detailed notes, which again we have enthalpy change, which is a heat change under standard conditions. We have breaking bonds is the energy taken in from surroundings. Forming bonds is the energy given out. When energy is taken in, enthalpy change is positive. When energy is released to the surroundings, delta H is negative. Delta H means bonds that you break minus bonds that you make. So positive minus negative. We have energy level diagrams that show energy taken in and energy given out during the progression of the reaction. So we have energy on the y-axis, and then on the x-axis we have reaction progression. For endothermic, we start from reactants being lower than the products, and then for exothermic, we start with reactions being higher in energy level than the products. And this is because for endothermic, energy is taken in to break the bond, and the opposite happens in exothermic reactions. So delta H would be positive in endothermic, so that's why it's going up. The arrow is going up, and then the exothermic, the arrow is coming down, so it's a negative delta H. Activation energy is more for endothermic reactions than it is for exothermic reactions. So again, for endothermic, heat is taken in, so delta H positive, and the opposite way around for exothermic reactions. In calorimetry, we have experimental method to find delta H by measuring delta temperature over time. We could use the equation Q equals MC delta T, which is energy is mass times specific heat capacity, usually 8 point something. It's given in the equation times the temperature change. We have specific heat capacity, which is defined to be energy required to raise 1 gram of a substance by 1 Kelvin without changing the state. So enthalpy change per mole is usually the follow-up question that comes after this, and it's delta H equals Q, which is MC delta T, over moles, which is mass over MR. It's measured in joules per mole. In calorimetry, we have sources of errors that happen really often because calorimetry is never completely accurate, as energy is always lost to the surrounding. So heat loss could be due to convection, conduction, or inaccuracies in measuring temperatures, and it could be reduced by putting a lid on the calorimeter or insulating the outsides of the calorimeter or using a polystyrene cup. So for C, we usually take H2O's specific heat capacity, not the actual solution, and this leads to further inaccuracies. So for Hess's law, we have energy in a reaction system is conserved and cannot be destroyed or made. So overall enthalpy change is independent of the route taken, and it's always the same. So in this triangle, AB equals ACCB. So the energy is independent of the route. So we have enthalpy change of formation on Hess's triangle. That arrows point from the central product C up to A and then B, because A and B are both formed from the products of C. So delta H of T equals delta H1 2 minus delta H1, which is again solved like vectors. And then the enthalpy change of combustion is arrows point down towards central product. And it's always H2O and CO2 for combustion, and again it's solved like vectors. So bond enthalpies are averaged values, so their energy required to break 1 mole of a stator bond in gaseous state under standard conditions, which again is 100 kilopascals and 298 kelvins. So data booklet values are usually averaged values because each calorimetry varies in each situation and isn't exact, so we take an average. We have mean bond enthalpy being the change when 1 mole of a specific covalent bond is broken, average out across the other range of the compound. So this relates to how strong a bond is, used to decide which bond would break first in a chemical reaction. Bonds with lower enthalpy values are expected to break first. Reactions that require breaking many bonds or are endothermic overall occur slowly in room temperature. And then topic 7, we have boiling temperature, which is the temperature of a substance changing state from liquid to gas. We have hydrogen bonding, which is the interaction between a hydrogen atom and an electronegative atom. And then we have nitrogen, fluorine, or oxygen bonding with the H. So the slightly positive hydrogen is attracted to the lone pair on the electronegative atom, being the nitrogen, fluorine, and oxygen, and the hydrogen bonds are stronger than any of the other bonds, such as London forces or dipole-dipole forces, but weaker than ionic and covalent bonds. So we have intermolecular forces that exist between molecules. The strength of the intermolecular forces impact the physical properties such as boiling point or melting point. Then we have permanent dipole-dipole forces, which is when molecules with polar covalent bonds interact with dipoles in another molecule. So stronger than London forces but weaker than hydrogen forces. Then we have polar bonds, which is a covalent bond between two atoms in which electrons are bonded together but unevenly distributed. This causes a slight change and a difference, which induces a dipole in a molecule. Then we have a solvent, which is a liquid that dissolves any other thing in it and forms a solution. We have van der Waals forces, or known as London forces, which are instantaneously induced dipoles. They exist between all molecules, and they arise due to fluctuations of electron density within a non-polar molecule. These fluctuations may temporarily cause an uneven electron distribution, so therefore an instantaneous dipole. This dipole can induce a dipole in another molecule, and this goes further on. So we have three types of intermolecular forces, which are van der Waals, known as London forces, dipole-dipole bonds, or permanent dipole bonds, and hydrogen bonds. Okay, so the van der Waals is the weakest. It's also known as instantaneously induced dipoles or London forces, okay? And it depends on the MR of the molecule and its shape. So the larger the MR, the greater or stronger the intermolecular forces. And then long chain carbohydrate hydrocarbons actually have more intermolecular forces than branched hydrocarbons, and this is because the distance is actually less, making the force stronger. And then we have boiling trends in alkanes. So alkanes are CnH2Ns, 2n plus 2, so they're saturated. So van der Waals in alkanes are affected by the chain length and the branching. So if you have a higher chain length, you have higher MR, so you have higher intermolecular forces of attraction, so the boiling point and the melting point increase as a result. But then if you have branching, you have low London forces, because less tightly packed together, so distance increases, weakening attractive forces, lowering the boiling point and the long chain alkanes. So permanent dipole acts between molecules of a polar bond. So we have delta positive and delta negative of neighboring molecules attracting each other, holding the molecules together, forming a lattice-like structure. So polar bonds form due to the difference in electronegativity. Like Cl is delta negative, H is delta positive, because they are very different in electronegativity. So hydrogen bonding is the strongest one. It acts between hydrogen, fluorine, oxygen, and nitrogen, and the lone pair of these atoms forms a bond with delta positive of a hydrogen atom from another molecule, shown with a dotted line in the diagram. So they all have hydrogen bonding. So properties of hydrogen bonding is high melting points, high boiling points compared to similar sized molecules without hydrogen bond. So like water is unusually high boiling and melting point because the size is actually similar to many others, but it has a really high boiling point due to the presence of hydrogen bonds. And it requires a lot of energy to overcome and break the bonds. So hydrogen bonds cause ice to have lower density than water, although it's the solid version, so it should have had more density. And this is because H bonds hold molecules in rigid structure with lots of air gaps, so they're more separated, therefore lower density. So hydrogen bonds cause alcohols to have higher boiling points than alkanes because they have an OH bond. Because lone pair electron on oxygen is able to form a H bond with the hydrogens on the other alcohol molecules. So solvents that are usually H2O contain H's, so H bonds. So H bonding allows it to dissolve ionic compounds by dissolving individual ions. And then it dissolves some alcohols by forming H bonds with their hydroxyl groups. But both H2O and alcohols are polar solvents to dissolve polar molecules such as halogenoalkanes, so it cannot form hydrogen bonds. Then we have non-aqueous solvents, which are used for compounds that have same intermolecular forces. So this is also well known for like dissolves like. And then we have boiling trends of hydrogen halides. So as you can see, HF is way higher than HCl, HBr, and HR. And this is because it's the only halide that forms a H bond. So it would have a higher boiling point than London forces or permanent dipoles. And then the boiling point increases as you go down the group after HF because halides increase in size number, so number of electrons increases, so more van der Waals forces, so more energy required to break the bond. And then we have topic 8. So it's redox, group 1, 2, and 7. So we have disproportion reactions, which is a species in both oxidized and reduced. So both increase and decrease in oxidation number of that species. And then we have half equations, which is a full redox reaction. Hello.